element of the adjacency matrix. Right, so in this case, the adjacency for directed graph is defined as such. As you can see, the element of the matrix is equal to 1 if there is an edge connecting between I and J. And the element is equals to 0 if there is no edge connecting between VI and VJ. The number of ones in the adjacency matrix of a directed graph is equal to the number of edges. Now look at this example. You are given directed graph as such. Now the graph involves 5 number of vertices, therefore the adjacency matrix is of dimension 5 by 5, 5 rows and 5 columns. Now focus on the first row of the matrix A. The first row of matrix A is representing V1. Connection between V1 to all other vertices in the graph. The first column represents V1, second column represents V2, and so on. Now, since there is no loop in the graph between V1 to V1, therefore the element of A11 equals to 0, and from the graph you can see there is one directed edge from V1 to V2, therefore A12 will equals to 1. Similarly, V1 to V3 is connected by one edge, and therefore the element of A13 is equals to 1. This is how you find the element for the first row of matrix A. You can use the same procedure to find element of the matrix, especially for the rest of the row. Incident matrix for undirected graph with no loops. Incident matrix is different with adjacency matrix, whereby the row in the matrix represent the number of vertices, while the columns of the matrix represent the number of edges. So, here the dimension of the matrix is n by m, where n is the number of vertices and m is the number of edges. Consider that the incident matrix is represented by C, where the element is Cij is equals to either 1 or 0. It is equals to 1 if vertex Vi is incident by the edge Ej, and it's equals to 0 if vertex Vi is not incident by the edge Ej. Now look at this example to illustrate how to obtain the incident matrix for the graph. And this graph is considered undirected graph with no loops. Now, the number of vertices in the graph is 1, 2, 3, 4. Therefore, the number of rows in the incident matrix M is also 4. Consider the first row to represent vertex 1. Second row represent vertex 2. Third row represent vertex 3. And the fourth row represent vertex 4. And remember, to find the number of columns of the matrix is depending on the number of edges in the graph. So in this graph, the number of edges is equals to 5. Therefore, you can have 5 number of columns in the matrix M. Therefore, the dimension of the matrix M is 4 by 5. The first column is considered to represent edge number 1, second edge number 2, number 3, number 4, and number 5. Now, let's see how to calculate or how to obtain the entry of the first row for incident matrix M. The first row of the incident matrix M representing the first vertex V1. From the graph, you can see that V1 is incident only to E1 and E4. Therefore, V1 E1 is equals to 1. V1 E4 is also equals to 1. Other than that, it will equals to 0. For second row of the matrix M, we will focusing onto the vertex V2. This is the vertex V2, and from the graph, as you can see, V2 is incident to E2 and E3. Therefore, the element of second row of the matrix M, especially V2 E2, is equals to 1, V2 E3 is equals to 1. Other than that, it is equal to 0. You can use this procedure to fulfill or to find the entry for the third row and the fourth row of the incident matrix M. Now that we move to find the incident matrix for directed graph. Remember, the number of rows in the incident matrix is the number of vertices in the graph, while the number of columns in the incident matrix is equal to the number of edges in the graph. But in this case, for directed graph, the element of the matrix is either 1, -1, and 0. Why? It is simply because in the directed graph, it involves direction in their edges. We can have direction going into one vertex or direction going out from one vertex. If there is an edge going into one vertex, let's say this is vertex I, then you can have that Cij is equals to 1. Okay? If Vi is the initial vertex of Hej, if Vi is initial vertex of Hej, is simply described as the edges that is incident to vertex Vi with direction out from vertex Vi. So in this case, Cij will equals to 1. If the direction is into the vertex Vi, then the element of the matrix is equals to -1. If there is no edge attached to vertex Vi, then the element is equals to 0. In this case, the direction of the edge is matters to determine the entry of the matrix. Here we give you one example how to obtain incident matrix for a directed graph. Consider this graph. This graph involves 4 number of vertices labeled as V1, V2, V3, and V4. Therefore, the number of rows in the incident matrix M is equals to 4. First row representing vertex V1, second row representing vertex V2, third row vertex V3, and the fourth row vertex V4. Number of edges in the graph here is equals to 5. Labeled as E1, E2, E3, E4, E5. Therefore, the number of columns in the incident matrix is equals to 5. The first column representing edge E1, followed by E2, E3, E4, E5. Now that the dimension of this incident matrix M is 4 by 5. Now look at the first row of this matrix. Let's see how to calculate or determine the entry of this first row. We are focusing on the first vertex V1. Look at the graph. This is the vertex V1, and as you can see, V1 is incident to only 2 edges, that is E1 and E5. Other than that, V1 is not incident to E2, E3, and E4. So from the first row, you can have element of V1 E2 equals to 0, element V1 E3 equals to 0, element V1 E4 equals to 0. While element of V1 E1 equals to -1. Why it is -1? Because the first thing, E1 is incident to V1, or V1 is incident to E1. But the direction of E1 is into the vertex V1. from the definition, if the direction is into the vertex, then the element will equals to -1. Similarly, E5 is also adjacent to V1 and the direction of the edge E5 is into V1. Therefore, the element of V1 E5 is equals to -1. You can use this method to fill up the entry of second row, third row, and the fourth row of the incident matrix M. I hope you enjoy the explanation on finding the metric representation of the graph. We will see you then in the next topic.